Section 13.6 Equilibrium in Saturated Solutions. Until now, we've looked primarily at equilibrium in systems that involves gases. However, there are two also equilibrium systems that involve aqueous saturated solutions between solid solutes of slightly soluble salts and their ions. Everyday examples of solubility in equilibrium in solution are found in the slightly soluble salts that are found in bone and kidney stones. Bone is composed of calcium phosphate, which produces ions during bone loss. Kidney stones are composed of calcium salts such as calcium oxalate. Solubility product constant expression. In a saturated solution, a solid, slightly soluble salt is in equilibrium with its ions. As long as the temperature remains constant, the concentration of the ions in the saturated solution is constant. Let's look at the solubility equilibrium for the equation calcium oxalate, which is written with the solid solute on the left and the ions in the solution on the right. The solubility of a substance is the quantity of that dissolves to form the saturated solution. We represent the solubility in a saturated aqueous solution of solid calcium oxalate by the solubility product K sub Sp, which is the product of ion concentration. As other heterogeneous equilibria, the concentration of solid calcium oxalate is constant and is not included in the solubility product expression. Ksp is the concentration of calcium ions and the concentration of oxalate ions. In another example, we look at the equilibrium of solid calcium phosphate and its ions, calcium and phosphate. Calcium phosphate break apart into calcium and phosphate ions. As with other equilibrium expression, the molar concentration of each product is raised to the power that's equal to the coefficient in the balanced equilibrium equation. For this equilibrium equation, the solubility product expression consists of the concentration of calcium ions raised to the power of 3 and the concentration of phosphate ions raised to the power of 2. Solubility product constant. The numerical value of the solubility product expression is the solubility product constant, or K sub Sp. In this text, solubility will be expressed as the molar solubility, which is moles of solute dissolve in 1 liter of saturated solution. The calcium of a solubility product constant is shown in sample problem 13.9. Molar solubility. The molar solubility, S, of a slightly soluble salt is the number of moles of solute that dissolves in 1 liter of solution. For example, the molar solubility of cadmium sulfide is found experimentally to be 1 times 10 to the negative 12th molar. Because cadmium sulfide dissociates into cadmium and sulfide ions, they have a concentration equal to the solubility S. If we know the Ksp of a slightly soluble salt, we can determine its molar solubility, as shown in sample problem 13.11. Effective solubility of adding a common ion. We have seen that when a slightly soluble salt, such as magnesium carbonate, dissolves in water, small amounts of magnesium ion and carbonate ion are produced in equal quantities. When we calculate the molar solubility of magnesium carbonate from Ksp, it is 1.9 times 10 to the negative 4 molar, and the concentrations of both magnesium ion and carbonate ion are the same. We know from Chatelier's principle that adding one of the products to a system at equilibrium causes the equilibrium to shift in the direction of the reactants. The same principle applies to the solubility of a slightly soluble salt. For example, we can decrease the solubility of a slightly soluble salt, magnesium carbonate, by adding a salt that dissolves completely to give one of the ions magnesium or carbonate. When magnesium chloride is added to the above solution, it increases the concentration of magnesium ion, the common ion. Because the KSP for magnesium carbonate must stay the same, some magnesium ion combines with the carbonate to form solid magnesium carbonate. This reverse reaction decreases the concentration of carbonate ion and decreases the solubility of magnesium carbonate. So by adding an ion that's common to the slightly soluble, you drive the reaction back towards where it's hardly soluble at all. Suppose the magnesium chloride is added to the equilibrium mixture to give the concentration of magnesium equal to 1.10 times 10 to the negative 2 molar. Using the K sub SP, we can calculate the new solubility of magnesium carbonate, which is equal to the concentration of carbonate ion. K sub SP is the concentration of magnesium times the concentration of carbonate is 3 times 10 to the negative 8. K sub SP is the concentration of magnesium times the solubility constant equals 3.10 to the negative 8. We substitute the known concentration of magnesium and solve for the concentration of carbonate, which is equal to the new molarity constant. We rearrange the equation for S and solve for the molar solubility S, which is the amount of magnesium carbonate that can dissolve when a common ion has increased. So S is now 3 times 10 to the negative 8 divided by 1.0 times 10 to the negative 2, which is 3.5 times 10 to the negative 6. Thus, the new solubility S is reduced to 3.5 times 10 to the negative 6 molar for magnesium carbonate compared to 1.9 times 10 to the negative 4 when there is no common ion added. The solubility of magnesium carbonate can also be decreased by adding sodium carbonate, which increases the common ion carbonate. According to Le Chatelier's principle, the addition of the product carbonate causes the equilibrium shift in the direction of the reactants, which means it decreases the solubility of magnesium carbonate. In the reverse reaction, the common ion carbonate combines with some of the magnesium ion in the solution to form solid magnesium carbonate, which reduces the concentration of magnesium and the molar solubility of magnesium carbonate. So, depending on which common ion is added, it's going to reduce the solubility and drive it back to the solid form.